Good afternoon, everyone. Happy Friday once again. We're really getting down to the wire here. After today, we only have 2 more weeks of new material. I hope that you've had a great week, and I hope that everybody's still doing good. Today, we're going to be looking at lesson 31.17, which deals with integration by substitution. And this lesson can be found on page 16 of your handout. I've already mentioned this, but I'll try to drive it home again today. When you are talking about integration, which is anti-differentiation, we don't have a set of rules. We don't have a rule for integrating a product or a rule for integrating a quotient. Instead, what we have are strategies or techniques. And it's very important as you learn each of these strategies that you understand when the strategies are probably going to be useful. So when do you use this strategy or technique of substitution? You use it if one piece of what you're trying to integrate is contained within the derivative of the other piece. And that is a very slippery idea. We're going to require a lot of practice to get used to this. What I'm saying is, if you take a piece of what you're trying to anti-differentiate and you differentiate that piece, if the other piece is contained in what you get for the derivative of the first piece, then substitution is probably going to work. For example, if I said to you, what is the integral 2x over the square root of 3 minus x squared dx, you note that the derivative of 3 minus x squared will contain 2x. 2x is a piece of the derivative of 3 minus x squared. Very specifically here, if I differentiate 3 minus x squared, I get negative 2x. And negative 2x contains 2x, the other piece. I want you to note here that the piece of the derivative that we differentiate to get something that contains the other piece, the piece that we differentiate does not include the square root. This is a very important idea. When we talk about a piece whose derivative contains the other piece, we do not include the operation. We only include the argument. And we're going to go through a number of examples to try to drive that home. So as a warm-up for each of the following, identify the piece, and we always call the piece that we're going to differentiate that contains the other piece, we always call that piece u. So what can I choose in this first integral for u so that the derivative of what I choose contains what I didn't choose? Well, the answer is I'm going to choose u equals 2 minus sine x, because the derivative of that will be negative cosine of x, and that contains the cosine of x at the beginning of this integral. Notice that when I choose the piece that I will differentiate, I did not include this operation of raising to the 5. I only included the argument. If we jump ahead to the third example, because the second one is even more slippery than the others, what we can choose for the piece to differentiate so that the derivative will contain the other piece is t cubed. And notice that we did not choose e to the t cubed. We only chose the argument. So you don't choose the operation, you choose the argument. Now, before I talk about number 2, I want to take this a little bit further. If I were to differentiate in the first situation, find the derivative with respect to x, I would get negative cosine of x. And if I were to differentiate here the derivative with respect to t, I would get 3t squared. And what is important is that the part that was not chosen is contained inside of the derivative of the part that was chosen. Over here, the part that was not chosen is contained within the derivative of the part that was chosen. We're not going to worry just yet about that 2 in our integrand in the third case, and we're not going to worry about the fact that there's a negative in our derivative in the first case. The variables that you didn't choose from the integrand have to be contained as variables in the derivative of what you did choose. And believe me, I've taught this year after year for a very long time. I know how difficult this is. What some of you are going to discover at the end of all of this is that you don't need substitution to do these. And we'll talk about that later. Now, what am I going to choose for u, which is the piece I'm going to differentiate that will contain what I didn't choose for u? I'm going to choose x to the half. And it's going to be this x to the half. And the reason for that is when I differentiate this with respect to x, I'm going to get 1/2 x to the negative 1/2, but that's equivalent to 1/2 x to the half, and x to the half is root x. So what we end up with here is the derivative of what we chose is 1/2 multiplied by 1/root x, and 1/root x is contained within what we're trying to anti-differentiate or integrate. There's a 1/root x there. Notice again that just like in the first part of the warm-up, we didn't choose raised to the 5, and just like in the third part of the warm-up, we didn't choose e to the, we don't choose e to the here. So you want to choose something that's as big as possible for you, but it cannot include the major operation associated with that argument. And when you differentiate that thing you choose for u, it has to contain the other variable part of the integrand that you did not choose for u. Man, that's a lot to keep track of. Let's see how this works now. The basic goal is for you to use substitution to rewrite the integral with a different variable. And I will tell you right now, the variable is going to be u. It's possible to rewrite this integral as a different integral with the variable u. It's possible to rewrite this integral as a different integral with the variable u. And it's possible to rewrite this integral with u. And when you do that with substitution, the integral you get, which will be an integral of a function of u du, will be easier to integrate. In fact, it should be obvious in terms of how you integrate it. So this is our goal. You want to be able to rewrite an integral of f of x dx as an integral of f of u du. And you're going to use this strategy whenever part of f of x has a derivative that contains the other part of f of x. So let's look at examples now to get used to how this works. I want to integrate sine of x multiplied by 2 minus cos of x raised to the 5. And this integral has three ideas contained within it. One of the ideas is sine of x, one of the ideas is 2 minus cos of x, and the third idea is a power of 5. What we're going to do is choose the idea for u that is as large as possible but does not contain the major operation. And in this case, that's because if I differentiate 2 minus cos x, I get sine x, which is the rest of the integrand. Now, when you go from u equals 2 minus cos x, we're going to differentiate this now, but we're not going to write du dx. We're going to write du equals, and let's differentiate 2 minus cos x. The derivative of 2 is 0, minus the derivative of cos x is negative sine x. And by the way, I'm going to pause here for a second. We're not done. I'm going to pause. This is the thing that's a little bit weird. We are using differentiation to integrate, and you'll see how that comes together. But since we didn't write du dx, we have to write the dx on the other side. And we're going to play this game by moving the dx over for a reason that should become clear in about 2 minutes. What this means is that du equals sine x dx. And you certainly don't need to write the middle line. If u equals 2 minus cos x, then du equals sine x dx. But look at what we've just said. Du is sine x dx. Sine x multiplied by dx is the same as du. Well, over here, I have sine x multiplied by dx. That means that sine x multiplied by dx is du. And this is why it's called substitution. We are going to substitute in du for sine x dx, and we are going to substitute in u for 2 minus cos x. And what that's going to give us is a very simple integral to figure out. We're going to have the integral. Now the 2 minus cos x is u raised to the 5, and then the sine x dx, which is everything else, is du. This is like stealing candy from a baby now. What is the antiderivative of u to the 5 if u is the variable? Well, we increase the exponent by 1. We have to multiply by a 6th out in front, then we can add our constant. But now what we're going to do is, since u was 2 minus cos x, we can put 2 minus cos x back into this expression. And when you do that substitution, you get 1/6 multiplied by 2 minus cos of x raised to the 6 plus your constant. Now, to be fair, many of you may have been able to come up with this answer without using substitution. We had the integral of sine x multiplied by 2 minus cos x raised to the 5 dx. And many of you would have just reasoned out that, well, if I take 2 minus cos x and I raise it to the 6 and multiply by a 6th, that's going to work out because when I differentiate this, I'm going to have to multiply by the derivative of the argument of the power. In other words, I'm going to have to multiply by the derivative of what's inside, and that will give me the sine of x. And for that reason, many of you will be able to integrate most of the problems in this section without actually using substitution. You'll just use what I would call inspection or trial and error. Anyway, let's try another one. So this is a definite integral now, and we want to choose something for u so that when we differentiate it, we will get what we didn't choose for u contained in the derivative. All right, in this case, what we're going to do is choose u as being the argument in the major operation. That's almost always what happens. This is u. U equals x cubed minus 2x plus 3. So du is equal to 3x squared minus 2. dx. We want to somehow change everything else in this expression to u's. So we are already going to be replacing the part on the bottom with u to the 5 because we have x cubed minus 2x plus 3 raised to the 5, but x cubed minus 2x plus 3 is u. So the bottom is going to become u to the 5. What we have to worry about now is the top. And I notice that if I factor a 2 out of the top, I will have left 3x squared minus 2 dx. But 3x squared minus 2 dx is du. So this is the same as du. U is what's in brackets on the bottom, which means my integral now will be an integral of 2 du. This part was du over u to the 5. Now I've left the numbers 1 and 2 out of it just for the time being. This now can be written as 2 multiplied by the integral of u to the negative 5 du. And again, to anti-differentiate u to the negative 5 is very easy. I pulled the 2 out because it's not really relevant to the process of anti-differentiating. It's just a constant. What is the antiderivative of u to the negative 5? It will be u to the negative 4, and then we have to multiply by negative 1/4, and then we can put plus our constant. Although since we are going to evaluate the integral using numbers, we don't have to worry about the constant. So this becomes negative 1/2 u to the negative 4 plus a constant. But now we can substitute in what u was. U was x cubed minus 2x plus 3. Now let me explain to you why I removed the numbers 1 and 2. These numbers up here, the 1 and the 2, are referring to x. As soon as I write an integral with u, I can't use those numbers anymore. Now there's two things you could have done here. What you could have done is used u equals x cubed minus 2x plus 3 and put the values for x that I've highlighted in green in there to calculate values for u. And then whatever numbers for u you get, you could have put here and evaluated with those numbers. I prefer to actually just go with the original values, which are values of x. All right, so now we're ready to evaluate this. I have negative 1/2. That's just the constant, so I'm going to leave it out. Then we have x cubed minus 2x plus 3 to the negative 4. That is 1 over that quantity to the positive 4. And I'm going to have to calculate it at 2 and at 1 and subtract them. So I am going to have 2 cubed minus 2 times 2 plus 3. And I'm going to have 1 cubed minus 2 times 1 plus 3. Those are both raised to the 4. I get negative 1/2. I'm going to have 1 over 2 cubed is 8, plus 3 is 11, minus 4 is 7. I believe this will be 7 to the 4. We can check it on the calculator in a bit. Minus 1 over 1 minus 2 plus 3, I believe, is 2. So I'm going to figure out what 1 divided by 7 raised to the 4 is, and subtract 1 divided by 2 raised to the 4. By the way, I want us to just work in decimal here because I don't even think that number would be fractionable on your calculator. It isn't on mine, I don't think. It is a fraction, it exists, but my calculator just doesn't know what to do with it. Multiplied by negative 0.5, so my answer is approximately 0.03104. We can check this on our calculator by graphing that function. Let's see, on the top we have 6x squared minus 4, divided by, on the bottom we have x cubed minus 2x plus 3, n bracket raised to the 5. I don't think we want to concern ourselves with what this thing looks like. Let's just go zoom 6. I don't know what we're going to see here, if anything. I mean, it's a degree 15 rational expression. So what I want to do now is calculate the integral from 1 to 2. And you get 0.03104,175, and that is the answer that we got. It's not even shading anything in, so I'm not quite sure what this integral represents, but it's certainly not area. Just try a couple more. This is one that we've already looked at in the warm-up in terms of what to choose for u. We are going to choose this as being u. So if I have u equals x to the half, du equals 1/2 x to the negative 1/2 dx. Now let's start playing around with this integral. I'm going to take the fifth out because it's just getting in the way. We have an e to the root x, which will be e to the u, and then we also have on the bottom a root x, and we have a dx. Now let's take a look at our differential equation over on the right. We have du equals 1/2, and x to the negative half is 1 over root x. So this 1 over root x dx is contained within our differential equation. But it's not equal to du. It's equal to 2 du, because I have to multiply both sides by 2 to isolate that. I get 2 du equals 1 over root x dx. So 1 over root x dx is 2 du. This is e to the u. So it's all about substitution. We're replacing things that are described using the variable x with things that are described using the variable u. So this integral now is going to be equal to 1/5 multiplied by the integral of e to the u multiplied by 2 du. Well, that's pretty easy, but to make it even easier, we can move that 2 out in front and have 2/5 multiplied by the integral of e to the u du. Well, that's really easy because the antiderivative of e to the u, if u is the variable, is e to the u. So this is equal to 2/5 e to the u plus a constant. And now we go back to the beginning and we say, well, what was e to the u? E to the u would be e to the root x, because root x was u. So we get 2/5 e to the x to the half. And if you differentiate 2/5 e to the x to the half, well, let's do it and find out what we get. If I differentiate, so this is just a check with respect to x, 2/5 multiplied by e to the x to the half, you get 2/5 e to the x to the half, because the derivative of e to the is e to the, times the derivative of the exponent on x, the argument, which would be 1/2 x to the negative 1/2, plus the derivative of the constant is 0. So what happens here is the 2/5 multiplied by the 1/2 gives you 1/5. Then we have e to the x to the half times x to the negative half. Well, that is e to the x to the half over 5x to the half, which is what we were asked to anti-differentiate. So it worked. So this is the answer. One last example. It's a definite integral from 1 to e of the square root of ln of x over x. What I'm going to do in this example is choose for u the ln of x, because then the derivative of u is 1 over x dx. And the reason this is going to work is because 1 over x dx, which is du, is contained within the integral. So du is going to be the highlighted part, and the rest of the integral will now be an integral of u to the half, because it's the square root of the ln of x, but the ln of x is u. I'll just maybe highlight one more thing here to make sure that you get my drift. Ln of x is u. So we have root u, which is u to the half. The 1 over x dx is du. So we're going to replace the yellow highlighted part with du. And again, two things here. You're dealing now with an integral which is very easy to anti-differentiate. You take u to the half, you increase the exponent by 1, and then you divide by the new exponent. But the other thing I want to point out to you is this is no longer from 1 to e. That 1 and e refer to values of x. Since u is ln of x, you could certainly calculate ln of 1 and ln of e and use those for u. I don't like doing that. I find it confuses students. So let's anti-differentiate this. The antiderivative of u to the half is u to the 3/2 multiplied by 2/3 plus your constant. U was ln of x, so we have 2/3 ln of x raised to the 3/2 plus a constant. I guess since we're going to be evaluating it from 1 to e, I don't need to worry about that constant. So I will have 2/3. That's a constant. Let's leave that out. I'm going to have ln of e to the 3/2 minus ln of 1 to the 3/2. Let's see, ln of e is 1. Ln of 1 is 0. So we end up with 2/3 times 1 to the 3/2 minus 0 to the 3/2. Well, 1 to the 3/2 is 1. 1 minus 0 is 1, so we're left with 2/3. We ought to be able to check that on the calculator by graphing the original integrand. The original integrand was the square root of the natural logarithm of x. Make sure you close the brackets on that square root argument, divided by x. Again, I really don't know what this is going to look like, and I don't care. I'm just going zoom 6. There it is. And I want to evaluate that as an integral from 1 to e. And you get 0.6 repeating. which is 2/3. We've talked about this before. The number that your calculator gets is not exactly equal to the correct answer. And I don't know quite what the reason for that is. I suspect that your calculator is doing a calculation of area by splitting the area into a bunch of pieces and adding them together. Regardless, your calculator is not the correct answer. It's just used to confirm that we got the correct answer. I'll tell you, as a technique of integration, this is a very slick method, but it is one of the slipperiest ones to wrap your head around and get a good handle on. So on page 511, question 3, do not do R, and then 4, G, and H in question 4 are challenge problems. But I want, before we finish this off, to show you something. If you take a look at some of these I don't think require substitution. Let me highlight the ones where I would say to you substitution is overkill. Now, for some of you, substitution might be overkill for all of them. I don't know. Those two for sure are overkill. I think this one, substitution is not necessary. I think this one, substitution is not necessary. The ones I think substitution is not necessary for are ones that you could do just by using common sense. So let's take a look at C. C is the integral of x plus 6 raised to the 10 dx. Well, I know that's 1/11 x plus 6 to the 11 plus my constant. And you know what? I think all of you should know that too. There's nothing tricky about this one. And the reason why there's nothing tricky about it is what's inside x plus 6 has a derivative of 1. So you don't need to worry about it. Now, how would substitution be used? And this is why I say substitution sometimes is overkill. What you would do is say u equals x plus 6, which means du is dx. And now if we look at the original integral, I'm going to have the integral of, it's not going to be x plus 6 to the 10, it's going to be u to the 10, and then it's not going to be dx, it's going to be du. Well, that's 1/11 u to the 11. And then you put the x plus 6 back in, and you get the answer we got. Let's take a look at E. You have secant squared of 3x as an integrand. So we want the integral of secant squared of 3x dx. I would look at this and say, well, what do I differentiate to get secant squared? And the answer is 10 of the argument. But then I would say, oh yeah, but I need a third here, because when I find the derivative of 10, I will get secant squared. Then I will have to multiply by 3, and I don't have a 3 out in front of my integrand. Substitution would say u equals 3x, which means du equals 3 dx, which means dx up here is a third du, and your substitution is going to give secant squared of u times a third du, which is 1/3 integral secant squared u du. Well, the antiderivative of secant squared of u with respect to u is 10 of u, and we have that third in front, but u is 3 multiplied by x. So I think sometimes substitution can be overkill. That's a set of problems that you can be working on, both 3 and 4. I would definitely say to you that this is one of the trickier methods of integrating. When we look at the final 2 methods over the next 2 weeks, which are integration by parts and integration of rational expressions, you'll find them very easy. This is tough. So give it your best shot. If you have problems, get a hold of me and we can work through them. In the meantime, have a great rest of the day and enjoy your weekend, and we'll talk to you soon. Take care.